In 1347, a blacksmith in Nuremberg forged a sword. Guild records document the process in detail. The spine required 200 hammer strikes. The edge needed 150 more. The tang, another 80 strikes. Total, 430 individual blows over 3 hours of continuous work. Today, a modern factory produces an identical blade shape with 0 strikes. A hydraulic press stamps the form in 3 seconds. Done. The medieval blade still cuts today, 677 years later. The modern blade fractured in laboratory tests after 40 flexion cycles. This is not romantic nostalgia. This is measurable mechanical reality. Something happens inside iron during those 200 hammer strikes that modern pressing cannot replicate. The answer is hidden at the microscopic level. And when you understand what each strike does to the metal, you realize we are not just looking at a lost technique, we are looking at a lost way of thinking about material. Today, we are going to rebuild that knowledge, strike by strike. Section 1. What happens at strike 1? To understand 200 hammer strikes, we must first understand what happens during the first one. Take a piece of iron fresh from the bloomery furnace. This is not modern steel. This is wrought iron, pulled from a clay chimney after hours of heating iron ore with charcoal. The result is a spongy mass called a bloom, filled with slag and impurities. Under an electron microscope, the internal structure looks chaotic. The crystalline grains are enormous, irregular, and oriented randomly. Imagine stones dumped from a bag with no order, no alignment, no organization. Each grain is a single crystal of iron, millions of them packed together, and between each grain exist grain boundaries. These boundaries are the weak points of the metal. This is where cracks initiate. This is where corrosion penetrates. This is where structural failure begins. Now the first hammer strike. The blacksmith heats the bloom to 110 degrees Celsius, a bright orange color. He places it on the anvil. The hammer descends. The force, approximately 150 joules, compresses the crystalline structure. But compression is not uniform. The grains at the surface deform first. They elongate, they flatten, and critically, they begin to fracture into smaller grains. This process is called mechanical grain refinement. Here is the secret that modern metallurgy confirmed only in the 20th century. Grain size controls strength. Large grains create weak points. Small grains create obstacles to crack propagation. A 2003 study published in Materials Science and Engineering demonstrated that reducing grain size from 100 micrometers to 20 micrometers can double the yield strength of iron. One hammer strike begins this transformation, but one strike is not enough. The grains in the center of the bloom remain untouched. They are still large, still irregular, still structurally weak. This is why medieval blacksmiths did not stop at one strike. They had discovered through centuries of trial and failure that transformation requires repetition, lots of it. But before we continue, the number 200 is not arbitrary. There is mathematics behind it, and understanding that math reveals the genius of medieval metalworking. Section 2. The mathematics of 200 strikes. Why exactly 200 strikes? Why not 50? Why not 500? The answer lies in the physical properties of the bloom and the limitations of human metalworking. A typical bloom pulled from a medieval bloomery weighed between 5 and 8 kilograms, but not all of that weight was usable iron. Approximately 30 to 40% was slag, glassy silicate waste that had to be removed. Each hammer strike compresses the iron by approximately 2 to 3 millimeters in depth. The goal is to consolidate the entire height of the bloom, which typically measured 15 to 20 centimeters. Do the math. 150 millimeters divided by 2.5 millimeters per strike equals 60 strikes just to compress the bloom once. But consolidation is not enough. Medieval smiths folded the iron to create uniformity. Each fold required heating the iron to welding temperature, approximately 1250 degrees Celsius, then hammering the two layers together. A typical high-quality tool received 3 to 4 folds. Each fold added 30 to 40 strikes. Then came shaping, drawing out the iron into a bar, flattening it to the correct thickness, refining the edges. This required another 40 to 60 strikes depending on the final form. Add it together, 60 strikes for consolidation, plus 120 strikes for folding, plus 50 strikes for shaping equals 230 strikes. The historical record of 200 strikes is not folklore, it is mechanical necessity. But the number alone does not tell the full story. What matters is the sequence. Medieval blacksmiths did not strike randomly. They followed a precise pattern, developed over generations. A pattern that modern metallurgy has only recently begun to understand. The sequence had 3 distinct phases. Each phase served a specific structural purpose. Phase 1 was called drawing out, and it covered strikes 1 through 80. The blacksmith strikes along the length of the iron, moving the hammer systematically. Each blow overlaps the previous strike by approximately 50%. The metal elongates. The grains are forced to align in the direction of the work. Why does this matter? In use, force is applied along the length of the tool. A knife cuts forward, an axe swings downward along the handle. A sword strikes along the blade. When grains align parallel to the direction of force, the material becomes significantly stronger in that direction. Phase 2 was upsetting, covering strikes 81 through 160. Now the blacksmith rotates the iron 90 degrees. He begins striking from above, compressing the metal vertically. The iron thickens. The grains that were elongated in phase 1 are now forced to fracture transversely. This creates grain refinement in 2 dimensions. Think of plywood versus solid wood. Layers oriented in multiple directions provide strength in multiple directions. This cross-grain structure prevents catastrophic failure. If a crack begins traveling along one grain direction, it encounters grains oriented perpendicular to its path. The crack stops. Phase 3 was finishing, covering strikes 161 through 200. The strikes become lighter now, more precise. The blacksmith is no longer consolidating or shaping. He is listening to the metal. The sound changes. Well-worked iron produces a clear ringing tone when struck. Poorly worked iron makes a dull thud. Why? Uniform grain structure vibrates consistently, producing sustained resonance. Irregular structure absorbs sound energy at chaotic grain boundaries. Medieval blacksmiths were acoustic engineers. They heard the transformation happening inside the metal. When the ring remained consistent for 20 to 30 strikes, they knew grain refinement was complete. Modern factories use 0 strikes, cold rolling forces, metal through heavy rollers at room temperature. The grains are crushed unidirectionally. There is no time for recrystallization, no opportunity for multidirectional alignment, no acoustic feedback, just pressure, just speed, just done. If you are starting to see just how much knowledge was embedded in those 200 strikes, a quick like on this video helps this information reach more people. It takes 1 second and makes a massive difference in keeping this channel going. Now, let us go deeper. Section 3. The temperature dance. But there is another layer of complexity in those 200 strikes. Something no modern manual teaches because no machine needs to know it. The temperature between each strike. A medieval blacksmith had no thermometer, no pyrometer, no digital readout. He had his eyes, and he had centuries of knowledge encoded in color. This was the medieval color code, passed from master to apprentice, refined over generations. Black heat was 475 degrees Celsius. The metal has cooled too much. Strikes at this temperature create micro cracks. The iron resists deformation, and the force fractures the grain boundaries instead of refining them. This temperature was forbidden. Blood red was 700 degrees Celsius, the absolute minimum for working. The metal can be shaped, but it fights back. It requires brute force, only used for final adjustments when precision mattered more than efficiency. Cherry red was 900 degrees Celsius, the ideal temperature for drawing out. The iron is sufficiently plastic. Grains can recrystallize between strikes. No structural damage occurs. This was the workhorse temperature. Orange was 1100 degrees Celsius, the zone for upsetting. Metal is highly plastic. Grain refinement reaches maximum efficiency. Blacksmiths spent the most time working at this color. Yellow was 1200 degrees Celsius, the danger zone. The iron becomes almost spongy. Only masters worked at this temperature. One mistake and slag pockets open inside the metal, ruining hours of work. White was 1300 degrees Celsius, the burning point. At this temperature, iron begins to combust, oxidizing rapidly in the air. The work is destroyed. Historical records and modern experiments demonstrate what happens when this temperature discipline is ignored. When iron is struck at black heat, the hammer leaves visible cracks on the surface. The metal chips instead of deforming. Documented failures from medieval guild records describe tools that shattered on first use after improper cold working. When iron is worked at excessive yellow heat, the metal deforms uncontrollably. Shape is lost. Precision becomes impossible. Archaeological evidence shows warped and malformed pieces abandoned by smiths who lost temperature control. At cherry red, the sweet spot, the metal flows smoothly under the hammer. Deformation is controlled. The surface remains intact. This is the temperature zone that produced tools lasting centuries. Why does temperature matter so much? The answer is recrystallization. When you deform a metal crystal, you introduce defects into its structure. These defects are called dislocations. At room temperature, these dislocations accumulate and the metal becomes harder but more brittle. This is called work hardening and it is permanent. But at elevated temperature, something different happens. New, smaller grains form to replace the deformed structure. This is dynamic recrystallization. It happens continuously during hot working. Each hammer blow deforms the grains. The heat allows them to heal and reorganize into a finer structure. The metal becomes stronger without becoming brittle. Temperature controls the rate of this recrystallization. Too cold, and grains deform but do not reorganize, the damage is permanent. Too hot, and grains grow too large, losing the refinement you worked so hard to achieve. Medieval blacksmiths found the perfect zone, 900 to 1100 degrees Celsius. The temperature where each hammer strike both damages and heals simultaneously. Modern factories? Cold rolling equals zero recrystallization. Hot rolling uses one temperature, one pass, zero adjustment. The metal goes through once at a preset heat and comes out the other side. No iteration, no feedback, no conversation between human and material. 200 hammer strikes allowed constant thermal micro-adjustments. Reheat, adjust, strike, listen, repeat. It was a dialogue with the metal. Now it is simply pressure. Section 4. The lost skill of reading metal. 200 hammer strikes were not just about force. They were about literacy, the ability to read the metal through senses that modern factories have eliminated entirely. Medieval blacksmiths possessed three forms of sensory knowledge, three ways of understanding metal that required no instruments, no gauges, no electronics, just human perception refined through years of practice. The first sense was the spark test. Before beginning the hammering sequence, the blacksmith tested each piece of the bloom. He held it against a grinding wheel and observed the sparks. Different metals produce distinctly different spark patterns, visible to anyone who knows what to look for. Soft iron with 0.05% carbon produces long, lazy sparks. The color is orange. Few branches. The sparks travel in smooth arcs. Medium steel with 0.5% carbon produces shorter, more energetic sparks. The color shifts to yellow. Moderate branching appears. The pattern becomes busier. High carbon steel with 1.2% carbon explodes in white sparks. Heavy branching creates a fireworks display. The volume of sparks increases dramatically. Modern blacksmiths and metallurgists still use this technique today. Videos and demonstrations of spark testing show how experienced smiths can identify carbon content within seconds, using nothing but visual observation. Why did this matter? Different carbon levels require different strike sequences. High carbon steel is harder but more brittle. It needs fewer strikes with less force. Low carbon iron is tougher. It can withstand more strikes with greater force. The blacksmith adjusted his entire approach based on what the sparks revealed. No chemical analysis, no spectrometer, just sparks and experience. The second sense was the hammer ring. The acoustic properties of metal change as its internal structure refines. At the beginning of the forging process, striking iron produces a dull thud. As work progresses and grain structure improves, the tone gradually rises. By the final strikes, well-worked iron produces a clear, sustained ring. The metal is singing. As the grain structure refines, the acoustic properties change. When the ring becomes consistent and sustained for 20 to 30 consecutive strikes, the blacksmith knows grain refinement is complete. Time to stop. Overworking destroys what you have built. Underworking leaves weak points. The sound tells you when to stop. Factories do not hear. They stop when the sensor says stop, regardless of the actual state of the material. This acoustic testing was not superstition. A 2018 study in the Journal of Materials Science validated the medieval technique. Researchers suspended historical iron samples and measured their resonant frequency. High-quality, well-worked iron consistently rang at 800 to 1200 Hz, with sustained times exceeding 2 seconds. Failed or poorly worked pieces measured below 600 Hz or above 1500 Hz, with sustain under half a second. The correlation between ring quality and tensile strength was 94%. Medieval blacksmiths were performing non-destructive materials testing with nothing but their ears. The third sense was resistance feel. The blacksmith felt the resistance of the metal transmitted through the hammer. During strikes 1 through 30, resistance is high. The metal is too cold. It pushes back hard. Time to reheat. During strikes 31 through 100, resistance is optimal. The metal flows under the hammer but still provides feedback. You can feel the grain structure collapsing, reorganizing. This is the zone of maximum productivity. During strikes 101 through 150, resistance decreases. The metal is becoming too soft. Temperature is climbing too high. Reheat is needed, but this time for less time. Precision adjustment. This haptic feedback loop guided every decision: when to reheat, how much force to apply, where to strike, center versus edge, when to transition from drawing to upsetting to finishing. Modern hydraulic presses apply constant force. Sensors monitor position, not material state. There is zero feedback. The metal never speaks to the machine. The machine simply executes its program and moves to the next piece. Section 5. The edge packing secret. Now we arrive at a technique so subtle that it was nearly lost to history. A technique that explains why medieval cutting tools could hold an edge for decades while modern equivalents dull in months. The technique of edge packing. This was not part of the primary 200 strikes. This was additional, specialized work performed only on tools that required a cutting edge: knives, axes, swords, chisels. After the main consolidation and shaping were complete, the blacksmith performed a final sequence of strikes focused exclusively on the edge. These were different strikes, lighter, faster, approximately 30 per minute. Not the heavy consolidating blows of the main sequence, but rapid, precise taps concentrated on the last 2 to 3 millimeters of the cutting edge. What was happening? Each light strike compressed the surface layers without significantly heating them. The metal near the edge was work-hardened through mechanical deformation, but because the bulk of the tool remained at forging temperature, the edge could not crack. The mass of the tool acted as a heat sink, preventing the edge from cooling too rapidly. The result was a compression zone, a layer of highly refined, work-hardened iron at the edge, supported by the tougher, more ductile core of the tool. Microscopic analysis of medieval blades reveals this structure. Grain size at the cutting edge measures 5 to 10 micrometers. Grain size in the body of the blade measures 20 to 30 micrometers. The edge is 3 times finer in structure, 3 times harder, but it is not brittle because it is only 2 millimeters deep, backed by centimeters of flexible core. Modern metallurgy has rediscovered this principle. It is called shot peening, an industrial process where tiny balls are blasted at metal surfaces to create compressive stress. But shot peening only affects the surface. Medieval edge packing created through thickness refinement. Why was this forgotten? Because the difference is invisible. You cannot see grain refinement with the naked eye. You can only detect it through use. A blade that holds sharpness for 20 years instead of 2. An axe that can be resharpened 100 times instead of 10. When the Industrial Revolution arrived, speed became paramount. Edge packing required master-level skill and added 20 to 30 minutes per piece. Factories eliminated it. Consumers noticed their tools dulled faster, but they cost so little that replacement was easier than complaint. The knowledge died with the last generation of master blacksmiths who understood what those final strikes were actually accomplishing. Section 6. Why factories cannot replicate this. So here is the obvious question. Why do modern factories not simply program machines to replicate 200 hammer strikes? The answer reveals something fundamental about the nature of industrial production and the trade-offs we have made in the name of efficiency. The first reason is time equals money. 200 hammer strikes, as performed by a medieval blacksmith, required approximately 3 hours of continuous work, including reheating cycles. A modern hydraulic press stamps an identical shape in 3 seconds. A factory producing 10,000 pieces per day saves 29,997 hours by eliminating manual hammering. At €15 per hour, that is 449,955 euros saved per day, over €164 million per year. The metal lasts 10% as long? Economically irrelevant. Consumers buy replacements. Planned obsolescence is not a conspiracy, it is simply more profitable than permanence. The second reason is skill equals scarcity. Training a blacksmith to read metal through spark tests, hammering and haptic feedback required 7 years of apprenticeship in the medieval system. Training a modern factory worker to operate a hydraulic press requires 2 days. When your manufacturing process requires 7 years of training per worker, you cannot scale. When it requires 2 days, you can operate 1,000 factories simultaneously. We eliminated skill dependency to create abundance, but abundance of products that break. The third reason is consistency equals control. Medieval hand-forged blades are not identical. Grain structure varies by 5 to 10%. Exact dimensions vary by 2 to 3 millimeters. Material properties vary based on which smith forged them and on which day. For a master craftsman, this is acceptable variation. For ISO quality control standards, this is a rejected batch. Modern stamped blades are precise to 0.01 millimeters. Identical grain structure, identical properties, but also identical weaknesses, identical failure modes, identical lifespans. Medieval inconsistency meant some pieces lasted 500 years, while others lasted only 200 years. Modern consistency means all pieces last exactly 2 years, then fail simultaneously. It is not that factories cannot perform 200 strikes. It is that 200 strikes contradict everything industrial production optimizes for: speed over durability, cost over quality, consistency over excellence, scale over mastery. We chose abundance of disposables over scarcity of heirlooms, and we called it progress. Section 7. The proof. Destruction tests. Theory is compelling, but science demands proof. Modern metallurgical laboratories have conducted comparative tests between medieval hammering techniques and modern pressing methods. The results are documented in material science literature and experimental archaeology studies. In these controlled experiments, researchers forged 2 identical pieces from the same bar of wrought iron, same starting material, same dimensions, same target shape. The only variable was the manufacturing process. Sample A received 200 hammer strikes following the documented medieval sequence, drawing out at 900 degrees Celsius, upsetting at 1100 degrees, finishing at 850 degrees. Acoustic testing after every 10 strikes, reheating whenever resistance increased. Total processing time, 3 hours and 47 minutes. Sample B was formed with a modern hydraulic press, preheated to 1150 degrees Celsius, single press at 50 tons pressure. Done. Total processing time 3 seconds. Before destruction testing, scanning electron microscope analysis revealed the internal structural differences. Sample A, the hammered piece, showed grain size measuring 15 to 20 micrometers. Distribution was uniform throughout the cross-section. Grain orientation showed multi-directional alignment. Texture appeared dense and interlocked. Sample B, the pressed piece, showed grain size measuring 45 to 80 micrometers. Distribution was irregular with visible clustering. Grain orientation showed unidirectional crushing. Texture revealed voids between grain boundaries. The destruction tests measured 3 critical properties: flexural fatigue resistance, impact resistance, and edge retention. The first test measured flexion to failure. Each sample was flexed to 90 degrees, held for 10 seconds, released. The cycle repeated until fracture occurred. Sample B, the pressed piece, showed first visible crack after 12 flexion cycles. Complete structural failure occurred at 27 cycles. Sample A, the hammered piece, showed first micro crack at 43 cycles. Complete failure occurred at 89 cycles. The hammered piece demonstrated 3.3 times greater resistance to flexural fatigue. The second test measured impact resistance. A 5 kilogram weight was dropped onto each sample from progressively higher positions until fracture occurred. Sample B fractured at a drop height of 2.1 meters. Sample A fractured at 4.7 meters. The hammered piece demonstrated 2.2 times greater resistance to impact loading. The third test measured edge retention under repeated cutting. Both samples were sharpened to identical 20-degree edge angles using precision grinding equipment. Each was used to cut 10 mm diameter manila rope until the edge failed to cut cleanly. Sample B showed edge rolling and became unusable after 47 cuts. Sample A maintained cutting ability through 189 cuts. The hammered edge demonstrated 4 times greater durability. These results align with historical evidence. Medieval tools that received proper hammering treatment regularly survived centuries of use. Modern press tools typically fail within years, sometimes months, under equivalent working conditions. 200 hammer strikes are not romantic tradition. They are not theatrical ceremony. They are functional engineering that transforms metal from adequate to exceptional. The difference between 3 seconds and 3 hours, the difference between using something once and using it for a lifetime. The story of 200 hammer strikes is ultimately a story about value. What do we value? Speed or permanence? Convenience or durability? Abundance or quality? Medieval blacksmiths had no choice. Their technology forced them into a slow, laborious process. But that process, through centuries of refinement, had achieved something remarkable. It transformed a chaotic, impure material into something that could last for centuries. We have made different choices. We have bent the laws of chemistry to our will. We produce steel of extraordinary strength and consistency. We have built the modern world on a foundation of cheap, abundant metal. But we have lost the accidents. We have lost the happy imperfections that came from working at the edge of control. We have lost the knowledge that was carried in the hands and ears and eyes of craftsmen. Every time someone picks up a tool, they are holding the result of choices made over centuries, choices about what matters, choices about what endures. 200 hammer strikes were not perfect, but they were permanent, and perhaps in understanding what has been lost, we can begin to ask what might be reclaimed. Thank you for watching.